This is problem 4-52M. It's on page 235. A square stud, 200 millimeters long and 8 millimeters on a side, is made from titanium. They give the specifications there. That's so we can go look up material properties. What angle of twist will result when a wrench is applied in a pure torque that causes the stress to equal the yield strength of the material in shear? Well, why don't we go and find the yield strength of the material in shear first of all, and see what it looks like. Let's go to the back of the book. There's got to be some properties of titanium back here somewhere. Let's see, material properties begins on page 714. There's stainless steels on the next page. Titanium and its alloys, I bet this is it. Alpha beta alloy Ti6A14V. Yeah, that looks like the one we want. It says that it's aged. Yeah, there's properties for aged here. So this is A15 continued. So let's see what these columns are. There's ultimate strength, yield strength, density, percent elongation, elastic modulus. Why don't we grab the yield strength while we're here? And we'll grab the, no, we won't bother. If we get the elastic modulus E, we'll have to calculate G from it. And there is actually a relationship between the two, but I don't see Poisson's ratio in here, so I don't think we'd be able to calculate it. Hopefully G will be in the chapter. But anyway, the yield strength for, that's going to be the third column, well, we're in metric units, so that'll be the fourth column over. So 1, 2, 3, 4. Looks like it's 1070, and it is megapascals. Everybody see where I got that? Okay, so now let's go back into the, there we go. Titanium alloys, table 4.3 has it. Looks like G, the shear modulus, is 43 gigapascals. Notice we've got a small problem. The yield strength that's listed is not the yield strength in shear. Those are two different things. This is the yield strength when you're just trying to pull something apart, not when you're shearing it either by a force directed along the cut surface or a torsion. So we have to somehow come up with this strength. Well, go back, let's see, let me find the page for you. Go back to page 202 and look at the top of table 4-1. And you'll see that the design strength is listed as the yield strength over 2N. Why is it over 2? Notice that this is a shear, whereas this is a normal stress, or normal strength. Okay? Well, the design factor is N, but basically this 2 factor is to convert the strength of the material in normal stress to the strength of the material in shear. They haven't mentioned a design factor, so basically the yield strength in shear we're going to estimate as just the normal yield strength over 2. Does that make sense? So if we take this and cut it in half, let's see, we should be able to do that. 535 megapascals will be our yield strength in shear. Make sense? Okay. Okay, so what angle of twist will result when a wrench is applied? And now the thing is that the stress is being set equal to this. So the actual stress, tau, the maximum stress, is being set equal to that by just constraint in the problem statement. Okay? But they're asking what angle will result. Well, what equation should we use? Well, the equation we use is exactly the same as what we use for circular sections. The only difference is that J is a little different, right? So it's the torque length over J, but I don't see torque anywhere. So what torque should we use? Well, how about this one? Okay, so we'll use tau max, which we have a number for, is equal to T over Z peak. Okay? So let's plug that in. Let's get rid of T. T is equal to tau max ZP. Let's make that substitution and see what happens. So tau max ZP L over G, J. We're getting close because we know the value of tall max, we know the length, I think that was given, wasn't it? Yeah, it's 200 millimeters. And all we need is J and ZP. So let's see if we can find that. So if we go back to the table, let's see, looks like it's cut off in these slides. Yeah, it's cut off. I don't remember the table number, but it's the table for non-circular sections. What page number was that, guys? Do you recall? 247?
27.
227, thank you. So for the sake of the video, it's figure 4-27. What are we dealing with here? We're dealing with a square section, right? And so J is 0.1418 to the fourth, and ZP is 0.208 A cubed. So we can make that substitution. Tall max, we're almost done. ZP is 0.208 A cubed. L over G. J is 0.141 A to the fourth. Notice most of the A's go away. But what is A anyway? It's the side length of the metal stud. So if you look at the figure 427, you'll see that A is that side dimension which they gave us was 8 millimeters. So now let's plug everything in and see what we've got. Maximum shear, 535 to make it easy times 10 to the 6th pascals, which is newtons per meter squared. Takes care of this term, times 0.208, because it's not a round cross section. L, the length of it was 200 millimeters, so 0.2 meters. Divided by G, we looked that up and found that it was 43 times 10 to the 9th pascals, so newtons per meter squared, times 0.141 times A, but A was 8 millimeters, which is 0.008 meters. Okay, I'm just converting all the units so everything will come out right. Let's make sure 1, 2, 3, yeah, that would be 8 millimeters. The newtons per meter squared will cancel, the meters will cancel. That's a good thing. This is coming out dimensionless like we expect. So plug all these numbers in your calculator. I'll make it easier on you. The 10 to the 6th can cancel with all but 3 of the 10s on the bottom. Okay, so that's 10 to the 3rd now. So now you can type it in your calculator. It should be a little easier. So 535 times 0.208 times 0.2 divided by 43,000 divided by 0.141 divided by 0.008 is how much? 0.46. Anyone second that? 0.46 radians? Okay. Now convert that to degrees if you would please. Let's multiply by 180 over pi degrees per radian. How much?
26.3.
26.3 degrees. That seems like a pretty large deflection to me. I don't know if we did something wrong or if that's just the way it's set up, but anyway. Maybe that makes sense because the material is being stressed all the way to its yield point. So maybe that's why. Questions, comments? All right. Have a good weekend, guys.